All right. Hello, everyone. Uh, so welcome to Little Red Riding Hood and the Forest of KD Trees. This is actually a talk I've been wanting to do for a very long time. Try to, steal inspiration from a lot of the other good talks that I've seen both here and other places. And it's also on a topic which I find interesting. It's kind of a mix of it's a war story. I've been trying to articulate the observations and learnings I have encountering a new to me data structure and some of the code tricks that you have to do once you start getting into the dirty details. So it's my journey from hearing about it, from getting curious, until and to me this has served as just a playing ground to get into the sticky situations where you need to apply good and bad code techniques in order to get out, right? So what's in this talk? That's really it. It's my journey. So it started when I was asked a question that I didn't know the answer to, and obviously there was an answer, right? Because I thought about it for a long time and it stumped me. And it turns out there is an answer, and I wanted to just learn more about it. So it's an arena for me to play with implementation and to play with code. And I just call it my KD tree journey, right? So mouse pointer, I'll just get that away. All right, so why the odd title though? I find fairy tales deeply, deeply fascinating. It's one of the things that just everyone know, right? So who here has heard of Little Red Riding Hood, right? That's about as many hands I expected to see. Everyone knows them. And they have this sort of collective ownership. There's no clear author. They come in many, many variations. I'm pretty sure that if everyone here told their version of Red Riding Hood as they remember it, we would have as many versions as we have people, right? And they touch something very deeply human in us. They tickle some curiosity, and I think there are a lot of parallels to how we look at code. So yeah, they're told and retold. They've always been a vehicle for morale, for learning, for teaching. The familiar form makes room for play, and they transcend time and place. So there are some disclaimers that we have to go through first. There will be a lot of code in this talk. Some of it has been modified to fit on slides, so if it doesn't compile or if it's a little bit dense, then it's to fit. There will be some bad puns. I'm hoping for at least one groan. And there will be some spoilers. So if you don't want the ending ruined, I suggest you leave. So Hood. This is her, right? I've seen her many times. She's this innocent girl who is tasked by her mother to go visit her gran, right? In some versions she brings wine, in others she brings cakes. I think the wine is the most popular in the south. Maybe cakes are more popular in northern Germany, I don't know. On the way, she meets the big bad wolf, who tricks her into telling her where she's going. It's a big mistake. And she also distracts her, so maybe it's a good idea to give her a bouquet of flowers and bluebells. That'd be lovely with the basket of treats. She ends up getting eaten, and then, to no credit of her own, gets rescued. But there are a bunch of variations of these, and some of them are a lot less savory than the PG-13 version, right? Themes from this story is found all over Europe. And being in Norway, of course, you find it even in Trimskvida. When Thor loses his hammer, it gets stolen, and he has to dress up like a bride and ends up punching a lot of giants in the face, right? But it's the same story of dressing up as something else to get close enough to, deliver the killing blow. Today I say the canonical story is probably German. It's the Grimms, right? There is also an earlier record that is also written down by a Frenchman, but I can't remember his name. But the story and theme is just found everywhere. One thing I find interesting about this is that it's always recognizable. This one is by Doré. He will show up a couple of times. These pictures will be, I'll weave them in throughout the talk. for no particular reason other than they're beautiful. We should take some time to admire the amazing array of beauty that our world has to offer. But notice that they all depict scenes from the same story. They look nothing alike, but you instantly recognize exactly what is going on. You get the full story, right? Even though they're completely different, you can tell they're kind of the same. We as programmers are always, we're always telling ourselves to not reinvent the wheel, right? But why do people keep making paintings and drawings of red? And is that bad? I think we should invent wheels more often. This is red. I think we should invent wheels more often because it allows us to play with layout, with emphasis, with new coding techniques. And Matteus's talk on units is actually a good example because it's also this massive testing ground, right, for testing out C++ 20 features. And just to emphasize the value of storytelling, the collapse of the typing rebellion and my subsequent wanderings to avoid the deadly clutches of the vengeful imperial agents form the basis of this narrative. A narrative whose very existence and use of the first person pretty much ruin any sense of suspense that might have made it worth reading. This is from the Bulwer Lytton competition. I recommend everyone to just go to that website and read through all the winning entries. They're fabulous. Okay, so let's talk about trees. This is the Japanese and probably also Chinese word for tree. It's ki in Japanese. So the problem I was posed was, given a set of points, p, with a value, so you have your xy coordinates and an associated value, and a radius r. What's the average value of all the points within this radius r, that point for every point in P? Please solve it. So this is actually a pretty easy problem. It's actually even easier to state if you do it graphically, I think. It's just what's the average value of the points in the circle, right? So how do you do that? So this is how you would do it in Python, right? For given points, like you look at all the points, you compute the distance. If it's within, you consider it, and if not, you throw it away, right? If you put it into the bigger program, it looks like this. You just, bring them along. So anyone want to take a stab at the performance and complexity of this? This is not a trick question. Anyone? Yeah? All right, so it's squared, right? Counter loops. Can you do better? Right? This is obviously a leading question. Yes, you can do a lot better. I didn't know how, so this was new to me. It's very intriguing. So it turns out there is a data structure. It's called a KD tree. Has anyone ever written one? No? There's one. Good. Anyone used them? You've written, used. I mean, I guess if you've written, you've used, right? Anyone ever used a KD tree? I think a lot of you have. You just don't know because it powers database engines and a lot of games use it. Anyone ever heard of a KD tree before? See a few more hands. Okay. Well, the rest of you are a part of our lucky 10,000 today because this is an amazing data structure. So what do you do when you're completely stumped, but you get this hint that you can use a KD tree? Well, you go to Wikipedia, and this is what you get. So the KD tree is a binary tree in which every node is a k-dimensional point. Okay. Every non-leaf node can be thought as implicitly generating a splitting hyperplane that divides the space into two parts known as half-spaces. Points to the left of this hyperplane are represented by the left subtree of that node, and points to the right hyperplane are represented by the right subtree. Hyperplane direction is chosen the following way. Every node in the tree is associated with one of the k dimensions, with the hyperplane perpendicular to that dimension's axis. Thank you, Wiki. So I read that. I think I read this section maybe 30 times. And so you know what this reads like? Do you know what this reminded me of? A monad is just a monoid in the category of end-of-functors. What's the problem? I mean, technically everything that section said is true, and it's completely and utterly useless unless you're already familiar, right? So good on Wiki. I should actually probably fix that, but I haven't gotten around. But what I learned is that it has some amazing features, right? So it's a space partitioning data structure. That much I think we got. And it supports fast nearest neighbor searches, range searches, or in particular in databases you do when you do searches on multiple keys. For instance, give me the set of employees with this salary and age combination, right? And especially the nearest neighbor search in this machine learning K clustering age is a pretty, appealing feature. So then what do you do, right? So you have this interesting data structure that has some other properties that you want. So you start inventing the KD tree, right? So I figured the best way to actually understand this is to implement it. And I found little, I even looked up in Corman. Corman doesn't have KD tree, at least in my edition. So that was a bit disappointing. So what do we do? So when we're implementing something like this, what do we do? Well, we know it's a binary tree, so we start out with a binary tree, right? So if you look up in Corman, this is what a binary tree looks like. So ignoring some of the mumbo jumbo, you have three properties, right? Or three fields. You have the point for this node, and a left and a right subtree. And we don't want to leak memory, so we use the unique pointer, right? So this is a binary tree as you'd find in any computer science textbook, and this would be very good in the 80s. So this is going to serve well. This is where I started. And I figured I need some tools, so I need a way to check if two nodes are in range, right? So I wrote this in range. So this uses the trick where you square both sides, just to check right, this is faster than doing the square root. And then on Wiki, you actually get a pseudocode construction algorithm. This doesn't read too bad, right? So you pick your axis by doing def mod k, where k is the number of dimensions. You select a median, and then you recurse and partition the set, and then recurse left and right depending on whether or not it's larger or smaller, right? Okay, this is good because this is something we can implement. So this is what I started out with. For this talk, I have fixed k to be 2. This could be k, and it could be a template parameter. You can introduce it a lot of ways, but for now I'm just going to use 2. Okay, and now I have a comparison function that is axis aware, right? So every time you recurse, your depth is going to increase, which means that you're going to alternate between the two axes. And this is an easy way to integrate that into standard sort. So we pick the median by sorting and just picking one in the middle, not being too concerned about being odd or even. That doesn't really factor in for us. And then you recurse with make unique and repeat the process, right? So it's a pretty standard recursive construction. And this is fine, okay? So now we have the tree, presumably, and I did some testing where I tried to print it out, and it was a nightmare to follow. Because I still didn't really understand the tree at this point, but I figured this is more or less a mechanical transformation of the pseudocode, so hopefully it works. So I got into the nearest neighbor search, and it is very difficult, it turns out, through just Google to find a pseudocode kind of implement or denotation of the nearest neighbor search. I managed to find some lecture notes from, I think, University of Portland, where this is from. And I think there's a bug in it too, because I think it only considers the leaves, which has to be wrong, right? So this is what I found, that this is what it looks, and this is very much cleaned up from the notes that I stole them from. But we don't even want the nearest neighbor search in this case, right? We want the node in radius. So we modify it a bit and try and clean it up. And now we have the node in radius search algorithm, right? So I can say, all right, this is something that we can work with. So pretty much you have at whatever level you're at, you're checking your node against the one you're searching from and say, are you within distance, right? And if you are, then yield it. And if you're not a leaf, you probably want to consider the search tree, right? Or you need to consider the subtrees. So you check if you should go left or right first. Okay. And then you check some limits on the axis. And this was just, I never really found a good intuition or explanation for what these checks are, right? So I had to dig a bit deeper and do some drawings. But if you notice, you have two decisions in this algorithm. You have whether or not you should include a node and whether or not you should walk the subtree. Those are the two decisions that you need to make at every step. Okay. On the right there is a KD tree for this point set that has been constructed with, well, I mean, the way we've just seen. If you notice 7, 2, almost at the bottom there, if you count the number of nodes to the right of it, you'll see 2, right? And if you count the number of nodes or points to the left of it, you'll see 3, 5, 4, 2, 3, and 4, 7. There's a common way of visualizing this, which is this. This diagram is very difficult to get into if you don't have any experience. It's almost like the monad thing, right? But you can see how the space is partitioned by some axis to the node. And the trick, it turns out, is that within any rectangle, that's just a subspace of all the nodes. So you're kind of zooming in. One thing you'll notice at the end is that it kind of grows outwards diagonally from the center. But you can find all the nodes there, and you can see almost, if you try and trace it, how it works. Still not very good for the intuition, though. So I just removed all the lines. And this is still me just working on pen and paper, right? So I removed all the lines, and I just inserted 3 search points that are in blue. And this is just for the first partition. You can still see you have 2 nodes to the right of the red line, and 3 nodes to the left, right? The blue are just search points, they're not actually nodes in the graph. Okay. So we have 2 decisions. Do we include the node or not? And do we walk the subtree or not from this partitioning, right? So we're only considering this partitioning. And you can draw that in, because you just draw the radius around it. And this actually brings, so in order, whether or not you include the node, you just find the dots within the circle, right? That's pretty easy when you look at it like this, I think. You also include the ones on the edge, but you could choose to just discard them. Then there's the question, when do you walk the subtree? And this is the one thing I wish someone had stated pretty clearly, is that when you're at either of these, how do you choose whether or not to go into sort of the space partitioned on, or so let's actually take a very specific example. If you're at 6, 1 there, right? So you're considering that point and you're partitioning the space. Do you need to go right? Right? Yes, you need to, because the radius, the circle, cross the partitioning line at some point, right? That's it. There's no magic. But that is never really straight up stated unless in some hyperplane, mumbo jumbo. Okay, so whenever our radius, our search perimeter, crosses the partitioning line, that's when we need to go into the, let's quote unquote, other subtree, or that subtree. Well, okay, but how do we figure that out? And then it hit me after a lot of thinking that you really only need to check one point, which is the most extreme point on the circle, right? And where is that? Any immediate ideas? Probably figured it out much faster than I did. If you just follow the radius in the direction of the partitioning line, right? So in this case, you just follow them to the right. If that x coordinate is higher than the one the one that's the node you're considering, which is 7, 2, right? And then you go in there, and that's just a simple arithmetic check. Is it larger than some value? that is actually what the wiki thing said. All right, so now that we have that intuition, we can go into C++. So this is what I wrote, okay? So first you just get your left, right, and axis, just read out at every level, and you consider, is this in range or not? If it is, you write it. This is doing sort of output iterator style like the standard library, which I think is a good design. But if you notice the PQR axis stuff at, what's that line, 12 maybe? What it turns out you're able to do is you can collapse all of these into two checks by using the directionality of the signed integer regardless of dimension. So, I mean, obviously if you're going x in the x-axis, it would be left-right. But if you're partitioning in the y-axis, so you're horizontally slicing the space, then it would be up-down, and it would behave the same way. And that means that you can just take the point that you're at, and you can look at the axis, and you get the point at the radius in the right direction, not left-right, but correct direction, by doing minus if you're going to check if you're going to the left subtree, or plus if you're going to the right subtree. And that's it. I think that's actually super elegant. And you can see the symmetry between the two sizes, and that just gives us a radius check for nothing. It's very fast. Okay. So now we actually had an implementation that worked. I was very happy. That worked. So now I had the KD tree and an implementation that worked. And I needed to fix it because the implementation works, but it's not good, right? So let's talk about abstractions, and more specifically, let's talk about effective abstractions. Anyone know what this is? Not a trick question, I promise. Yes. It's a ball. Very good. Specifically, it's a cartoon by Picasso. It's made in the mid-40s, I think. Apparently, it hangs on the wall of Apple computers. But I find it pretty fascinating because it's just a few straight and some curved lines, and you can tell it's a ball, and it looks nothing like a ball, right? But it still has somehow managed to capture the essence. And that's how I like to think about abstractions too, is that you want just a straight and simple lines that, well, in Picasso's words maybe, is that even a child could draw, right? But to capture the essence of something. So I wrote this, which is kind of inspired by the standard iterators. It's not quite an iterator, but I'm going to use this the next time I'm doing a tree-based structure, that's for sure. I called it a view because it doesn't get to modify. It's similar to the zippers, if you're familiar with those from functional programming. But we now have this, it's technically a subclass, but we have this auxiliary class, right? With a dereference operator, two methods, left and right, and the Boolean conversion that just said, is this, essentially it checks, is this not a node anymore, which is when you've gone past the tree. Okay? This is, in the current implementation, is actually pretty useless. Okay? Do you know what this is? Pretty much relates to the previous slide. It's a pointer in a top hat. Thank you. So, because the structure now does nothing that the pointers don't already do. Here are some more of Picasso's sketches, and you can see he clearly knows how to draw a bull, right? But is it more a bull than the, well, simple one? Probably not. So we use this, and you can see the change isn't remarkable from the point of the query, right? Because pointers and trees, or tree edges as pointers, it's a pretty effective model already, right? Especially if you can name your members left and right. But they have the problem is that they're public and nasty, and you also need to do get because they're unique pointers. But overall, it doesn't look too different. So we get the left and right. It feels like there's a temperature mismatch, right? Because in here we have the mod 2, and when you recurse, you get the depth plus 1, right? But what I find interesting is that the view, it models all of the properties of the tree. So when you're at any node in a tree, you have a left binary tree specifically, you have a left child and a right child, right? That's what makes it a tree. And you can descend there, but you can't really go up. Okay. So I integrated the depth into the view, right? Which took out a parameter for the query. Query, by the way, is just the name of the neighbors in radius search. I stole the name from SciPy, who have a KD tree implementation, and they use the word query for this search. And this is actually much easier to use, because now you don't have to manually keep track of the depth, which you really only use to get the axis anyway. And guess who forgot to increment depth once? That would be me. Yeah, automation. I don't think this is an abstraction by getting the depth in there, but it is automation, and automation can be very useful. It gets a little bit better when you integrate the axis in there, right? So I think this is pretty easy to follow, too. Right? It's pretty neat. And more importantly, I think it sufficiently well models the essence of what a tree is, right? Okay, so so just to really drive that point home on modeling the tree properties, you have your left and right subtree, you capture the depth somehow, and you capture the fact that a node is a leaf or not. Okay, so let's talk about its representation. Oh yeah, by the way, this is actually a very effective abstraction, because after I did that that implementation, I never touched query again through all of the redesigns. Okay, so the query algorithm stayed unchanged, which is also very good for verifying and testing. Okay, so this is what it looks like now, right? With the unique pointer, the left and right, and some point. And you get the whole tree by chasing the pointers. There is a problem here, though, because, I mean, it's very slow. It's linear in the number of points in heap allocations, and it's just pointer chasing all over. And it doesn't feel very cohesive, even. So I managed to boil it down to the problem is that every node is treated individually. And in Corman, in computer science, that is true. Yeah, like any subtree is a valid subtree. You can, in theory, pull it out, right? All of that. In practice, that isn't a very useful property when you're writing programs, and you should consider this kind of like a collection, right? A collection in the vector or map sense set. So pointer-based trees are good for a lot of reasons, and when you need these properties, of course, you go for the pointer-based, right? Because they support fast splicing, so you just have two trees and you chuck them together by having some leaf point now, or make one of the leaf's children point to the root of the other tree or something. But splicing would invalidate a variant in a space partitioning tree like this, right? And it gives all kinds of lifetime issues, because who now owns the subtree? Can it still be used independently or not, right? The view, by the way, captures that. If you give someone a view to a subtree, they will think it's the full tree, and it will behave like in Corman. And I would argue that tree merges aren't very common. Like, your point set is probably pretty static, so you build your tree once and then you do repeated queries on that. And it comes down to this treating the nodes as independent and a part of a collection. Casey Muratori of Handmade Hero and Molly Rocket fame, he rants for days on this, and if you find that video, I recommend you see it. So I changed it to this, right? This is the simplest, most obvious mechanical transformation that you can do to make it into a collection, right? So you have to use the array unique pointer here. And this basically makes the KD tree thing a handle to some heap tree, right? you have to use the unique pointer because this is not a fully specified type yet. And and every node has your left and right subtree, but now as raw pointers and not as owning pointers. And then you allocate an array that's big enough and you just store all the nodes in there. This goes a long way. So construction cost just floored from that. Still not very good, but it's a huge improvement. But once you're here, you notice that you can do more. And I think there's this idea that improvements enable new improvements. So even though something immediately doesn't make it better, it can make it easier to make the next step, which will make it significantly better. And as you pull out the node type and really make the handle distinct from the node. So this node type actually now, they're all non-owning pointers because they know that they will be backed by some proper storage, right? And then you store the node in the array instead. So first of all, this is a huge performance improvement on destruction because now you don't need to check the storage pointer being null every time. And it's a 10-time performance in destruction, which is pretty amazing. And it also actually makes the total memory pressure slightly lower because you're storing one less pointer in the structure that is repeated, right? And now we're getting somewhere. Okay, but this still feels kind of off, right? Because now we're seeing that we have this handle and then the nodes, the tree itself, they're distinct, right? It's not the same type anymore. And really, this is feeling more and more like a collection, like vector. In the fairy tales, all things come in tree, right? So Hood, she was asked 3 questions, right? Or she was given 3 directions rather. And you come closer so I can see you better. And then she gets eaten. That applies in C++ too. And I think the fundamental problem with the previous implementation is that you can't copy it. Because you want your containers, your types really, to be, unless there is a really, really good reason not to be default constructible, copy constructible, and move constructible. And sometimes there are semantical reasons why that doesn't make sense, that you want to actually prohibit some of these operations, but for the most part, you want this to be true, right? And a good example of why is that then you can put it into other containers again. You can have collections of them. This is our situation now, because the unique pointer deletes the copy constructor, because it's unique, right? And that brings us to the rule of 3. It states that if a class requires a user-defined destructor, user-defined copy constructor, or a user-defined copy assignment operator, it almost certainly requires all 3. Okay? Well, now we need our custom copy constructor. So we write one. It's pretty okay. You count the nodes. In the copy, you allocate a new array, that's the right size. And then you just copy the nodes. Oops. This doesn't work. Now this doesn't work because we have a lot of pointers in the tree. And all of these, so this is what it looks like if you just take the same tree, but you don't consider only the values, but you consider the left and right child slots, pointers, right? This is actually a much better representation of trees. I don't know why the wiki doesn't use that. Again, I should maybe actually contribute it, because it makes it much easier to follow. If you take that tree and you just basically stretch it out as it is represented now in memory, which because it's just a contiguous array, right? It looks like this, and I've drawn in the pointers for convenience. And if you copy this, where do the pointers go? They still go back to the original structure, right? So just copying something like that naively is tempting, but it will crash, hopefully. Hopefully. So you need to do something more, and you end up with this monstrosity, right? So the first 3 lines are still the same. But then you have to run this loop through all the nodes to fix the pointers so they point into the copies that are in the new structure rather than into the original, right? So makes sense. It is very ugly. It's very ugly. And I didn't want to do that. This is something. This feels wrong, right? If you have to write this feels wrong. It's that something else is triggering, because right now it's required, but we don't want to be in a situation where this is required, right? I haven't mentioned anything about the assignment operator and destructor, but if you do this, you don't really have to define them, and the wording of the rule of 3 is that it almost certainly require all 3. In this case, you can still derive them because we're really delegating all the memory work to unique pointer anyway, right? So I think actually the rule of 3 in that sense is pretty outdated for practical purposes. We have the rule of 0. And the rule of 0 says that classes that do have custom destructors, copy move constructors, or copy move assignment operators, they should deal exclusively with ownership. Pretty much what that means that if you have to do anything that deals with ownership, that's the only thing you should do. You should factor that and only deal with ownership. Unique pointer is an excellent example of a class that does nothing but deal with ownership. I have to embarrassingly admit that I wrote that at some point now. And it made me reflect a little bit, because I realized that a lot of the techniques and a lot of the things that I did when I was experimenting and learning about this tree and using it as a playing ground for experimentation, I wrote a lot of code as I would have done 10 years ago, but with slightly different assumptions. And it actually ended up not being so bad. The KD tree is technically a binary tree, but it really stops there. They don't have any operations in common, and their external semantics are quite different. So I think the inheritance thing here is still nonsense. Don't worry about that. But you can design this generic binary tree storage thing that works, because the structure is then imposed on where do the edges actually go. So in what order, right? I ended up with something that looks like this, right? So instead of doing the inheritance, you do the composition, right? So I have this generic just tree storage, which should maybe be binary tree storage. And I supply the node type, okay? And I'm not going to go through the implementation, but it does the same fix-up thing in the copy constructor. So I just moved it out there. And this is what it looks like. Now, notice also I'm using vector of nodes rather than the array, unique pointer to array. And I'm pretty much just delegating the work of actually copying to the vector. It's great. So this works, okay? So now I have this generic tree storage that does the fixing of the copies, right? Oh, sorry, the fixing of the pointers post-copy. So let's talk about pointers. Can anyone tell what that is? It's not a trick question. Okay? So it's a bull, right? Technically, it's handlebars and a seat from a bike. But it's a bull. It depicts a bull. And you can tell and feel it's a bull, even though it looks nothing like a bull. But it has managed to capture the essence. Now, what are the essential properties of a pointers, right? Well, they're absolute addresses. They have support for arithmetic. They carry some type information, unless it's void, which is also carrying type information. And you can mark them as sort of unset. You have this special sentinel value in the null pointer. Okay. Which properties do we really use in this case? Well, turns out we don't really use anything. We don't use the arithmetic support really. We don't really use the type information. We do work because they're absolute addresses, right? What we do use is the unset. So I came up with this. What if you, instead of storing pointers, which are absolute addresses and has to be fixed up, you store offsets instead? This is Fortran. Right? This is what you would do in Fortran. This is one of the reasons why reading and dealing with Fortran is absolutely miserable. And it's a fantastic technique that is making a comeback. So what I did was I allocated, instead of one array, I allocated 3 arrays, or vectors, right? So one for the points, one for the left edges, and one for the right edges. And now you see you have this nice column, right? So on top you have the tree, but stretched out as it would be in memory. And then you can sort of, if you read the column, so if you take the first one, you see 72 has 2 children. One is at index 1, one is at index 4, and you can see the arrows at the bottom, they're the left children. The arrows on the top are the right children. So on the same for the 5, 4, it goes to 2 and 3, and -1 just means unset, right? Null pointer. Now what happens to the copy? Copy disappears because relative addresses are portable. It doesn't matter where your structure lives because all the addresses are relative. So you don't even need the tree storage, which is reasonably okay, but it was still a mess, right? So now you have 3 vectors, left, right, and storage, and that's it. It's super easy to copy, super easy to, it's relocatable, it's cheap to copy, and it's easy to serialize. That too is a pretty underrated property, because now you can actually send your tree pre-computed over the wire through just any serialization mechanism you'd like, because the addresses are relative. Just for reference, this is what the left implementation, and right would be the same way, looks like in the view, right? You just look it up in the left array at whatever position you're at, and then you make a new view for that child. Pass it on. Okay, so this is what it looks like. It has the default constructor, it has the copy constructor, and it has the move constructor, and they're all defaulted. You don't have to even specify them, but I included them just to be clear, right? Okay. Yay. So let's start gazing into the abyss. I stole this quote from Tony, who should have been here, but unfortunately isn't. Tony Fanard, he made I think maybe he did a talk 2 years ago called Words of Wisdom, but I don't think this is from that one. But it's pretty good advice. It's that abstraction does not stop at the class boundary. So I figured, yeah, gotta get me some of that. So I replaced, this is still in the construction, I replaced the axis/sort nonsense with 2 new private methods, right? Select pivot and partition in place. Partition in place because I don't want to actually have to make the copy and shuffle about, because there's a huge cost for no reason. And this is only done during construction anyway. If you put all that together and you look at the method or the full definition of the construction, it looks like this, right? So you select the pivot, right, and you partition it in place, and then you populate the left and right subtree based on whatever you have left in your input, right? I think this is pretty good because it does communicate the intent. First of all, this looks almost exactly like the Python thing, or sorry, the pseudocode thing from Wiki that we had 30 slides back. More importantly, you really have the intent instead of creating a lambda with some sorting and then doing some sorting and just picking some random element. Now you actually get what we're trying to accomplish, right? On top of that, what I think is good is it makes it much easier to play with alternatives. So I did this. Not very proud of it. So you see what's going on here? So less is, it's the same lambda, but done manually. And the reason I do that is because of this disgusting array in init less. So I pre-compute the lambdas or the comparison functions that would give me the sort, right? And then I just pick the one by looking up into the array on the second to last line, right? But you still need to initialize this at compile time. And that's not so pretty either. It looks like this. I'm not very proud of that. So I measured it, and this is a pessimation. It makes it slower. Which makes me very happy because then I definitely don't have to do it. I can only guess that it's because now it has to look up the numbers from memory rather than just injecting them into the instruction stream. But it gets a little bit scarier because what you can do is to move the axis parameter into a non-type template parameter. So this is sort of the compile time resolution of the same lambda. There's a slight speed up in that, but not worth, and also it increases the size of the binary a bit, so probably not worth doing either. But now that you're here, right, you can start playing with more alternatives because you can do dependency injection and strategies, right? So I made a strategy where I actually took the same select pivot and partition in place. And you pass this as a class template parameter to the class so that you can basically from the outside, you can do basically the wiring from the outside on how to select the pivot and how to partition. You need both of them to be in the same strategy because what you do with partitioning depends on whether or not, for instance, you sort internally in the select. So select can do it through sorting, in which case you don't want the partition to do any work. But I have to say, I wouldn't recommend actually doing this because I started thinking about it, and there are tons of variations on the KD trees. For instance, what you can do is you can take a trick from the B+ tree, and instead of in every node store just one point, you can store a block of points, right? And there are many variations. Or you can, instead of just doing mod depth to get the axis, you can, if you know that you're, for instance, going to have much more, like you're going to have a very flat but very wide spread out set of points, it might be an idea to partition twice on the x-axis and one on the y-axis, right? But this is not much easier to do because you've you pulled out and so this was I wouldn't have thought of doing that unless I had already written the select pivot and partition in place as helpers, right? So abstraction really does not stop at the class boundary. Also, I found that as a pretty good technique because once you get a collection of private methods that really only touch the same data and they're never touched outside of those, that's a pretty good hint that you can take that and extract it out anyway because it's almost independent of the rest of your class and you can treat it as a non-private dependency rather, right? So that's a pretty cool trick for identifying what to pull out of your big type. And that's where I stopped. So you can do many things from here, but this is where I chose to stop. But I'm very happy because I got to learn about the KD tree. It's a great structure. You can do so many things with it. And just being aware of it has made me realize there are a lot of problems that I can, solve with it and figure out how to weave into. So overall, it's been a very good experience for me. It's been a very rewarding journey. And I've had a lot of fun playing with code, right? There are some more fun experiments that I might figure out to do in the future. Actually, I did one of those. So what you can do is you can do implicit edge representation. So instead of keeping an array of left and right, you can, if you carefully, for instance, left balance your tree, you can do the indexing trick from heaps, where your root is on index 0, your left and right child are on 1 and 2, the left's children are on 3 and 4, the right's children are on 5 and 6, and so on, right? And you can use that. So I did that. That makes it very easy to copy, obviously, because it's just one big array. You don't have to deal with double lookups anymore, so it can be faster for some cases, but that forces you to have a very specific balancing to work. I would implement some more search algorithms, so obviously now I only did the in radius, which also takes it down from being squared to, so every lookup here is logarithmic, obviously, because it's binary tree, which, assuming it's well balanced. You can do more interesting pivot selections. So one technique I know is pretty common that gives reasonably balanced tree on average is to just sample a set amount of nodes or values. You pick the median of that, and now that's your partition key, right? And also other fun representations like bigger block sizes, maybe even varying. But you need to be careful because the view, in my case, has to match. It has to be aware of how the tree is constructed, right? But that's the relationship you need. So I would like to end on this note, is that as Granny sewed the bloody wolf pelt onto this stained red cape, Little Red downed another shot, reminding herself that even alcohol has a better taste than the gastric acid of a wolf. It's from the same competition. Thank you. I'm happy to take questions if there are any. If not, we can go have some coffee. All right. Thank you.